Thank you very much. First of all, thank you for inviting me to speak in this nice workshop and to have the chance of sharing the program with such distinguished speakers. Today I'm going to try to describe quite briefly, in fact, because the time is very short, the main activities that we carry in my group in the field of microwave photonics. I'm going to go straight to the point. So I will give a very brief description of the group and elaborate a little bit on the research activities that we carry, and that will take about one half of the talk, a little bit more probably, and then I will comment on our innovation and technology transfer activities. Right. We are about 25 people in the group, roughly, and we carry out research, as you will see in a few minutes, in three main areas, and basically these 25 people are led by the senior research team. These are my colleagues, to whom I also acknowledge part of the material that I'm going to present here. So, to give a first overview, our big picture, we carry research in three main areas. Of course, the oldest one is microwave photonics. It's historically the first and probably the most developed, and that reflects in the number of sub-areas where we are actually working. As you see, there are five main sub-areas, which I will describe briefly in a few minutes. But then we have again other two active areas. One of them is also quite extended in time, which is fiber-based photonic devices, in particular fiber Bragg grating-based devices. We probably have one of the very few academic labs in Europe that still can fabricate fiber Bragg gratings with full flexibility. And we, of course, we use them for microwave photonics as well, and for other applications like optical fiber sensors. And we have started about 5-6 years ago a new research line on photonic integrated circuits. Not all of the sub-areas are related to microwave photonics, but some of them actually do have a relationship, and I have highlighted them in the red color in the view graph. Okay, so I'm going to spend some time describing the microwave photonics area and the photonic integrated research area. And this view graph gives you a general portrait of what is the mission and how we envision how to carry out the objectives. And the way we work is basically reflected on the circle diagram that you have on your right-hand side of the view graph. It means that we start with trying to solve an application in the context of radio over fiber or microwave photonics. Probably it's driven by another application area like sensing. And we first try to come with a solution for that, a design solution, either in fiber-based format or integrated version or whatever. And then we try to build it with either on our own or with the collaboration with other partners. And these are some of the main partners with whom we have been working in the last years. And then the cycle is closed with a test. Inside the cycle, you can see how do we actually exploit our results, which is, as you may expect from a scientific or academic institution, by scientific publications and probably some patents. But we have a very strong vocation towards technology transfer. And in most of our research areas, there is a spin-off company as a result. In this case, as I will mention later, there's a new spin-off which is still it's going to be launched later this year, which is called eFux, and I will tell you a little bit later what is the company about. Okay, we have a similar approach for the photonic integrated circuit area. As you see, it's basically the same procedure. In this case, because we don't have fabrication facilities, we have to rely on external foundries. and that is part of our main collaboration part. And again, there is another spin-off company as a result, which is called VLC Photonics, and I will give you some more details in short minutes. Okay, so now let me try to describe more or less briefly, as I will try to do it as detailed as I can, bear in mind that I have a time restriction, the main research areas in microwave photonics. Probably the most important one that we're carrying now is integrated microwave photonics, because we envisage that as the only way that we have to make these systems widespread and at least increase their commercial penetration, which is now quite low. So we do this using two approaches. There is one research line in photonic integrated circuits, which is called PICs for microwave photonic applications, where the target is specifically to design integrated photonic circuits for specific applications, okay? Like I will show you specific microwave photonic applications. For example, the next view graph shows you a chip which is actually is a frequency discriminator. It's composed of a two-stage filter, and the first stage is just a bandpass separation, and the second stage is an elliptic filter which provides a ramp which is required for phase to intensity conversion. And the chip incorporates as well the photo detectors, and it's been designed in indium phosphide. And as I said before, we don't have fabrication facilities and foundries, so this was fabricated by HHI under the EuroPIC project. And this was a first attempt to do something a little bit more elaborated than purely modulation or something like that. And it turned out to be quite nice, working out quite nice in terms of performance, although we didn't get a really very high dynamic range value, but that was because it was a preliminary design, so there are many things to be improved. But once we had this circuit, and I'll show you again the layout with the contacts, etc. This is an indium phosphide, as I said before. We just realized that we could use part of this circuit as well to implement other functionalities. For example, the first part of the circuit can be employed to actually implement instantaneous frequency measurement circuit for radio frequency signals, and that is done by using the two outputs, two spectral outputs, complementary spectral outputs to implement an amplitude comparison function. And again, this turned out to work quite nicely, taking into account that the circuit was not designed on purpose for that application. Furthermore, we have used this circuit to implement a linear single sideband modulator based not on an amplitude modulator but on a phase modulator. A phase modulator is more linear than the amplitude modulator because there is no clipping, okay? But then what you have to do is to eliminate one of the sidebands to have the sideband modulation, single sideband modulation, and this can be done by placing this filter after the optical source. So at the end of the day, we realized that with one circuit we could practically implement at least three functionalities that are used in microwave photonics. And that led us to think about whether it would be possible to have to design a general purpose circuit which could include the minimum number of photonic and optoelectronic components and would be able to carry out most of the functions that are required in microwave photonics if those elements are adequately programmed. And this is the subject of one of our first research lines in integrated microwave photonics, which is to try to find out the architecture for an application agnostic architecture of a microwave photonic signal processor. Okay, what we have started working is on a possible starting configuration, which is one which is based on the optoelectronic oscillator architecture that you have on your left-hand side of the view graph. And this layout includes, the minimum number of elements. But the funny thing about that is that if you watch carefully and you elaborate this table with features of the different components, the modulator, the optical filters, etc., then you end up with the possibility of having implementing a lot of microwave photonic functionalities on the same chip. The question now is how to design this and how to implement that. Although I said before that we work in indium phosphide mainly, but we have also made designs on silicon photonics, but that would require a hybrid approach. We're still trying to decide which would be the best option. But this is part of one of our main research lines, and we hope to have a chip on this by the end of this year. We also want to explore about novel possibilities, and an alternative, an interesting research line is to try to research on the possibility of the advantages of incorporating graphene on top of silicon waveguides as a fastly tunable element to enable microwave photonic activities. And what you're going to see now is this is still not published yet, but this is a design of both a tunable phase shifter and a true time delay line, which is based on a double coupler resonator, where you put on top of the cavities a layer of graphene, and you can change actually the resonance position by changing the chemical potential of the graphene. And to do that, you need to put your waveguide structure. You have to carry out a full vectorial simulation to actually describe the behavior that you have on these results. And apparently this seems to be quite promising, and it opens the door to future tunable microwave photonic elements using graphene. Right. There are more research lines. Of course, the most important in terms of results is the one which was dedicated to signal processing, phase shifters, and two-time delay lines, which have led to world record results in terms of operation bandwidths, and also to novel results as this one which I'm showing you, which is the first microwave photonic filter that incorporates an integrated dispersive delay line, which is made with a photonic crystal waveguide. And that was a joint collaboration between colleagues from Thales and in France and our lab. Okay, we have activities also in fiber wireless systems, in particular with in OFDM systems, and also in the generation of arbitrary waveforms by exploiting our expertise in microwave photonic transversal filters. And this is a nice picture of a versatile bipolar ultra-wideband signal generator and distribution system along an optical fiber system, an optical fiber link. And recently we have been started to work on a thing, another subject which we think is called to have an important impact in microwave photonics, that is the incorporation of spatial division multiplexing. We always try to use that technology that is commercially available for digital communications, try to exploit the features in radio over fiber and microwave photonics. And in this case, we want to try to exploit the advantages that both heterogeneous and homogeneous multicore fibers can bring to this field. Let me show you a very nice example of a heterogeneous, how to implement a sample tunable true time delay using an heterogeneous fiber. And in this case, you have to design your fiber in a way that each core is different and it provides a different dispersion profile. If you are able to do this, and then you can most certainly have a basic incremental delay among the different cores of a multi-core fiber, and that incremental delay can change if you tune the wavelength of the optical source. And this is the building block for many applications in microwave photonics, not only for true time delay lines, but also for other applications like tunable filtering, and of course for arbitrary waveguide generation, but also for analog to digital conversion, because you have a parallel configuration, which is quite interesting. We have also interest in using the multi-core fiber technology for the radio access network, and to try to exploit the parallelism that MCFs bring, not only to feed the different sectors of the antenna base stations, but also to feed the different radiating elements, which is something which is required in MIMO communications. All right. I think I'm going to skip that, otherwise I don't have time to go into the technology transfer. Okay, we have always interest in innovative applications, and I have some nice results about using microwave photonics for quantum key distributions, including a world record on the number of keys distributed in parallel, which is 40 quantum keys in parallel, in combination with classical channels as well. All right, so let's go into the technology transfer aspect of the group. Each of the three main research areas has led to a spin-off company so far. Okay, so the microwave photonics area has led to EFUX, sorry. The photonic integrated area to VLC Photonics, and the fiber vibrating to a company called ColdSense, which is for optical fiber sensors for structural, civil engineering, health monitoring activities. Now, VLC Photonics is a design house. It's a technology independent design house, which is specialized in, it uses a part of our knowledge, and is specialized on designing and prototyping photonic chips in either in indium phosphide but also in silicon on silicon photonics. Okay, the way it works is that it's like an intermediate agent between the customer, which is the system integrator, and the chip manufacturer, which is the foundry, and basically it provides different services and different possibilities, ranging from feasibility studies to custom application-specific photonic circuit designs, prototypes, characterization, etc. And it also works in close collaboration with the foundries, in the sense that they do develop photonic design kits which can adapt to the generic processors for each foundry. Okay, so I must say that the company has had around 10 to 50 customers so far, but very few from the telecom area. Okay, most of them have come from the sensor area, interestingly. Now, and let me conclude with the other company, which is EFUX, which is completely different. The approach is completely different, because this is a product-oriented company. Okay, and the aim is to design instruments for optical and OVRA solutions in order to carry out microwave photonics and radio over fiber measurement. That means to put an optical layout so you can exploit your RF components. And this is done by exploiting our long-standing experience as users. And one of the things that is going to be presented the first time is this S-parameter measurement system, which actually can be coupled to any vector spectral analyzer and can provide you the pass, the up conversion and down conversion to the optical part of the spectrum, and you can use that to measure any kind of radio over fiber system. Okay, and the best thing of all is that it's compatible with any of the existing platforms. So this is more or less our very fast, I'm sorry, and brief overview of the activities of our group. Thank you very much.
Let's thank Professor Capmany. Okay, let's take one or two questions from the audience. I am interested on the requirements, for instance, on the length and the pitch between the chords and the amount of cores you would like to have, for instance, on digital analog converter based on the multiple core fibers.
Yes. Well, it depends, because if you are going to exploit, for example, time stretching, for example, which is something you could do, actually you need a dispersive fiber for time stretching, ADC. You were talking about ADC. Okay. So the multi-core fiber naturally provides you with a dispersion, of course, because the cores are and it provides you with a parallel scheme that you need. If you've seen the ADC configurations, many of them end up by doing a spatial diversity. Okay, so you have it all on your fiber. Okay, so it depends, but it's usually typical ADC is it's like 4 channels, something like that. Okay. But you could go for more because a standard fabrication, for example, many Japanese companies fabricate like 7 core or even 19 core. You can always use the central core for other purposes. So you have an even number of channels, and then you can use your central core for doing other things, like, for example, synchronizing. Because at the end of the day, you also need to synchronize the low speed electronic ADCs that you have at the end of the link. So that can be, for example, an idea of how to use. Standard 125 cladding diameter and 7 cores will provide you with almost negligible crosstalk.
It's very exciting to see we can see in the future this type of concepts entering measurements equipment.
Okay, yes. It's a parallel. You have everything. Parallelism is brought by the multi-core fiber. You can use it not only for communication purposes, but for everything where you need spatial diversity.
Any question from the audience? No, be the case, we can talk to Professor Capmany also in the break. So thank you very much.
Thank you.